Yuanyuan is going to tell us about Raman scattering, spectroscopy of praseodymium 3+ crystal field excitations in a praseodymium zirconium oxide system. Thank you. And I'll let you know after 10 minutes.
Okay. Thanks for the introduction. Hello, everyone. My name is Yuanyuan. I'm a graduate student from Johns Hopkins University, and today I want to talk about crystal field excitations in praseodymium zirconate that reveals dynamic coupling to the lattice in the magnetic degrees of freedom. And before I begin, I'd like to thank my collaborators in the Institute for Quantum Matter. The single crystals were grown in the University of Tokyo Vanderbilt group in Rutgers, the DFT calculation. And we did magneto-Raman scattering measurement in MagLab. And this work is supported by Department of Energy and ICAM Travel Award. The materials we studied on is praseodymium zirconate, which is a cubic pyrochloro, where praseodymium and the chromium ions sit on two interpenetrating sublattices of corner sharing tetrahedra. The spin ice-like pattern was previously revealed by the quasi-elastic neutron scattering, and significantly more than 90% of the neutron scattering is inelastic, and which provides the evidence for the quantum fluctuations. But what distinguishes praseodymium zirconate from other pyrochloros is the presence of the structural disorder, even in the stoichiometric samples. And the reason inelastic neutron scattering result indicates the disorder in praseodymium zirconate can give rise to distribution of quenched transverse fields acting on the ground state doublet. And some theoretical work also suggests the disorder in praseodymium zirconate could induce the quantum spin liquid state. However, the origin and the distribution of the disorder is not clear so far, and we know that praseodymium 3+ is non-cramped ion, so the crystal field doublets are not protected by the time reversal symmetry. So we expect to see the splitting or burdening of the non-cramped doublets due to the existence of disorder strain or some other lattice effects. And the motivation of this work is to study the crystal field excitations of praseodymium 3+ with high resolution spectroscopy. Our experimental technique is Raman scattering of light. And basically, we use Raman scattering to measure the frequency difference between incident light and scattered light. And this is a scheme of our macro Raman setup, and it consists of a laser source, optical components, a Cassegrain objective, and a triple monochromator. And in our lab, so we are able to measure excitations from 1 electron volt to 1 electron volt with very high resolution, and the polarization result setup allows us to identify the symmetry of the excitations. This is the sample we used in this experiment, and we cut a thin plate with 1:1 orientation from the single crystal rod run by the floating zone technique. We performed measurements in the temperature range from room temperature down to 6 Kelvin. And we used two geometries to identify the symmetry. In x-axis polarization, the polarization of the scattered light is parallel to the polarization of the incident light, while in xy, the polarization of the scattered light is perpendicular to the incident light. This is the Raman spectrum we took at about 6 Kelvin. Red peaks are phonons and blue peaks are crystal field excitations. And in this talk, I will only focus on the crystal field excitations. Ideally, praseodymium ion is surrounded by 8 oxygens and forming this 3D local environment. And the GX4 manifold is expected to be split into 3 doublets and 3 singulates. Now here I present a comparison of neutron spectrum and Raman spectrum. In general, so they are in a great agreement. And both methods observe the transitions from the ground state to all of the excited states. But with better resolution, and we noticed that the doublets around 55 electron volt is split in Raman spectrum, and the 2 components of the doublets can be well separated by polarizations. And this splitting is a very common spectroscopic phenomena in rare earth compounds. but rarely reported due to the limitation of the resolution. It happens when the phonon branch meets the crystal field level with the same energy and symmetry, and known as the phonon crystal field coupling. And due to the limited time, I'm not going to explain the details today. And the next, I'm showing the temperature dependence of the Raman spectra. The crystal field excitations are marked by the green triangles, and the right figure shows the evolution of the positions and line widths as a function of temperature, except the transition from the ground state to the first excited state. And see all the peaks of crystal field excitations and softened by about 1 milliton volt, and the line width of the peak decreased on cooling. But if we zoom in the low frequency range and we prop the transition from the ground state doublet to the first excited state, and we can see a sharp asymmetric peak below 30 Kelvin, and between 30 and 100 Kelvin, and we can find where to find a double peak. And above 100 Kelvin, we can only see a very broad band. The Raman intensity can be understood by the convolution of the density of the state of the ground state and a Lorentzian function, which is determined by the natural line width of the singlet. And we obtain the density of state of the ground state by using a deconvolution procedure with an empirical Lorentzian function. The result shows a pronounced two-component distribution between 40 and 100 Kelvin. In figure B, we showed temperature dependence of the positions, line widths, and the relative spectral weight ratio. Based on this analysis, and we conclude the ground state doublet is remarkably split by about 1 milliton volt above 30 Kelvin. And the relative spectral weight of the high frequency component omega B decreases on cooling, and the temperature dependence is reversed to the thermal population. The strong temperature dependence of the splitting cannot be simply explained by the random disorder, and we suggest the origin of the splitting could be either the deviation of the local D3D geometry or the dynamic displacement of the praseodymium ion between a central position and an off-center local minimum. And this deviation or lattice dynamics is expressed on cooling. At high temperature, the system prefers the off-center position. We also applied magnetic field along the 100 cubic direction up to 14 Tesla at about 5 Kelvin. The local spins are aligned along the 111 EZ axis and forming this two-in-two-out spin ice configuration. The Zeeman effect will split the doublets as the magnetic field increases. And in this spectrum, I present the field dependence of the crystal field transitions. So generally, we observed all the transitions from the lowest energy state to all of the higher energy states. And the splitting of the ground states give a trend of hardening to all of these peaks. And so remarkably, so this small peak is the transition within the splitting of the ground state doublet. And here I extract the energy shift of each peak, and the solid lines are the calculated results only based on the single ion physics. The experimental data generally agrees with the calculation, but there is a little discrepancy for the transitions from the lower state to the high energy singlets. So in order to overlap these three lines, so we borrowed the ideas from the previous neutron scattering work with the existence of an internal transverse field due to some lattice effect, so we can improve the phase. The origin and the mechanism of the internal field is still under exploration. And so in summary, so we present a high resolution temperature and field dependent Raman scattering study of crystal field excitations in praseodymium zirconate. And we see a Raburnic interaction between the crystal field levels and the phonons, and we probe the splitting of the non-Kram's ground state doublet and indicating the static or dynamic shift of the President 3+ from the local environment. And the field-dependent measurements suggest a transverse field acting on the ground state doublet. And with that, I'd like to thank you for your attention, and I'm happy to answer any questions you may have.
Thank you very much. Okay, time for a few questions.
Pierce, maybe may I ask one?
Yeah, go ahead.
Thanks for a nice talk. Well, two interrelated questions. So it's obviously non-Kramers doublet, but presumably it's magnetic since you have a Zeeman splitting, correct?
Yes.
And what is the primarily J value that contributes to that non-Kramers doublet? Is it J equal 4, J equal 2?
Yes, it's J equal 4. Yeah.
Okay. And then the next related question is that presumably in order to see anything in Raman, the optical transition will have to be loud, going, let's say, from EG to a high-lying singlet, right? So that means, right, you must have done the crystal field analysis and you know what the MJ components are of each of those states.
Yes, so
for instance, hypothetically, imagine a single was in MJ equals 0 state, but your non-Kramers doublet is primarily, you said MJ equal 2, right? So then optically, this wouldn't be an allowed dipole transition. The fact that you see it presumably means it's allowed, correct?
Right, it's not a dipole allowed transitions. Raman scattering are not dipole active transitions. Maybe that answers the question.
Oh, but then how does the transition?
So it's right, it's two photon transition.
Right, but I always think of it as a sort of two process, one absorption, one the emission, and for both of them, I saw they need to be optically allowed. But you're saying no, it can be.
It goes through a high-lying virtual state. So
yeah.
I see.
That's the reason. Yeah.
Okay. Thanks.
Any other questions? Okay. Thank you very much. Very nice talk.